Good afternoon. Thanks for joining us. My name is Tom Douglas with RAECO, and today's webinar is on photoionization and photoionization detectors, or PIDs. Our guest host today is Werner Haag. He's the author of the PID Handbook, Theory and Applications of Direct Reading Photoionization Detectors. Currently, he's working as a Senior Applications Chemist for Ion Science USA. We thank him for his time, his knowledge, and we're going to allow for questions towards the end of the presentation, and you'll probably notice on the bottom of the GoToMeeting box on the right-hand side of your screen, there's an area to chat. So if you come up with questions during, please feel free to put a question in there, and we'll get to those at the end of the presentation. And with that, I'll turn it over to Werner. Thanks so much, Werner.
Okay. Well, thanks, Tom. Yeah, so I'm glad to be here. I hope everybody can hear me all right. Let me know if there's any problems with that. As Tom mentioned, I'm with Ion Science right now, but I've worked for Array Systems for many years. So I've been around the industry and tried to keep my information sort of general on a technical level and not on any particular product. Different products have different advantages and disadvantages. So I'm going to keep this on a level of sort of general PID information as much as possible. I studied in basic environmental chemistry at MIT in Tennessee for several years, doing basic research, and then I moved into private industry where we studied treatment processes, and then later on these types of handheld detectors useful for industrial hygiene, health and safety, and similar measurements. There's a picture of me so people can see who he's talking. I'll briefly go over the theory of operation, list some workplace applications, and show them latest improvements in technology, and focus a little time on measurement of benzene, which is fairly important for some industries. Here's how a PID works. There's a lamp that emits high energy UV light, and the energy, these photons represented here, are high enough to kick an electron off of some molecules. So the gas comes into this chamber here. The light goes perpendicular to it. The gas flow. Every now and then, a molecule absorbs the light, kicks off an electron, and then you have an electron and a positive ion. This occurs between these two grids. There's a cathodic grid and anodic grid. And so these charged particles then move to the anode and cathode and get measured in an electrometer. Simply, so the concentration of the gas is proportional to the electrical current, or the other way around. The current is proportional to the concentration of gas for the most part. Most of these molecules go right through and are not ionized, so more than 99% of the gas passes right through without being affected. Therefore, it is possible to use a PID, a handheld PID here, as a gas sampling device as well as a measuring device. So in some cases, people can use these to collect the sample onto a charcoal canister and compare the PID readings with the charcoal readings, or measure different things that the PID cannot measure when it's going through its sensor. That's the basic operation, fairly simple, just kicking an electron off and measuring the current that results. All right. The standard features, and here we're talking about PIDs that are handheld and portable, not your fixed PIDs or laboratory equipment. These PIDs measure many organic vapors and some inorganics. The readout is continuous with a response time typically on the order of a few seconds. That's the next point here. So the gas is flowing through the sensor at flow rates of on the order of 200 to 500 cc's per minute, and this gives us a pretty fast response time. The available lamps are typically the 10.0, 10.6, and 11.7 EV lamps, and I'll explain how those are used a little bit later. It is a non-specific detector, which means it will basically measure anything and everything that comes through that is detectable. So if you have a mixture of different compounds, you cannot tell which is which or how much of each you have unless you have some more information from maybe an MSDS or some other analysis that tells you what the ratios are of the different components. But the signals from different components will just add up to it and give you some total. So you really cannot distinguish in general how much of the various components that you have. Nevertheless, it's used often in cases where you know which compound you have. If you have only one component, then and you're sitting in a vat of methyl ethyl ketone, then you know that that's the compound, and then you can get an accurate concentration measurement. The newest, or actually most PIDs for a long time have had data logging capabilities and the ability to measure TWAs and cell values. I assume everyone knows what these abbreviations mean. Once again, I'm talking about portable handheld instruments weighing typically 1 to 2 pounds perhaps at the most. Okay. So those are your standard features. Now, what does it respond to? Aromatics, benzene, BTEX, toluene, those are amongst the most sensitive compounds. Iodine-containing compounds like methyl iodide, that's now being used as a fumigant, and methyl bromide, those are fairly sensitive components. So here, 4 pluses indicates very strong sensitivity, 1 plus is weak sensitivity, and minus means no response. Things that are easily ionized, compounds with double bonds, organic amine, nitrogen compounds, sulfides and recaptants, these are compounds with sulfur in them. Ketones like methyl ethyl ketone, nail polish remover, ethers and silicates, these are used as lubricants and solvents often. And then compounds like alkanes, those are in fuels, gasolines, esters, in perfumes, and various other applications. Alcohols, glycols, aldehydes used in manufacturing. Those are less sensitive but can be detected. Some inorganic compounds like hydrogen sulfide, ammonia, phosphine have weak sensitivity but can be detected. The compounds that are not detectable are small inorganic molecules like hydrogen, carbon monoxide, CO2, oxygen, nitrogen, cyanides, acids. The things that are present in air, of course, you don't want air to respond, or you couldn't measure the VOCs selectively. You don't want to have a huge interference by the air, oxygen, nitrogen, or you wouldn't be able to see anything that's toxic. Here's another schematic of how these systems work. The ionization energy is what I've listed here for these various compounds in increasing order. This is the energy it takes to kick an electron off of the molecule. And with a 10.0 EV lamp, you can measure anything with an ionization energy less than that, the energy output of the lamp. So I can measure all of these compounds beneath this blue line. The 10.6 lamp is the most commonly used lamp. It goes a little deeper into the UV and will measure everything below this line. So it would include isopropanol, whereas the 10.0 lamp would not include isopropanol. Likewise, the 11.7 lamp can go even deeper into the UV and measure things with ionization energies up to 11.7, including, in this case, chloroform and methanol, but it would not be able to see methane or nitrogen or oxygen because that has an ionization energy over 11.7. When you want to make general measurements or you have compounds that are hard to detect, like chloroform, then you might need the 11.7 lamp. The big drawback to these lamps is that their lifetimes are only about a month or 2 or 3 maybe, if you're lucky. So they need to be replaced. So if you're trying to measure hard to detect compounds like chloroform, you can use this lamp. You just have to be prepared to change the lamp out every few months. Conversely, if you are trying to be selective and you want to measure something like you have a mixture of isopropanol and acetone, you don't want to see the isopropanol, but you do want to see the acetone, then you can use the 10.0 lamp because now it rejects the isopropanol and only measures the acetone. So you can improve your selectivity by using a lower energy lamp. You can increase your detectability by going to a higher energy lamp. But most commonly, people stay in the middle and take their 10.6 EV lamp, which typically, if you keep good care of it, the lamps will last 3 years, maybe even more. Okay. Important to understand also is what a PID cannot measure. Increase the list here some more: hydrogen, CO, including things like ozone, SO2, chlorine, small acids. Here the ionization energy is just too high to measure, and in some cases you don't really want to have this interference, as I mentioned before, from things like nitrogen and oxygen. Other common requests we get are things like anesthetic gases like sevoflurane and fluorane. These are highly fluorinated compounds or don't have a lot of functional groups that are ionizable, and so their ionization energy is just too high for this system to work. So you need some other type of detector. Most nerve agents are or chemical warfare agents. Many of these have high boiling points, so their vapor pressures are not very high. It's hard to get them into the sensor by the simple pump method. Also, their exposure limits are in the parts per trillion range. Even the IDLH is in the typically in the parts per billion range. So the PIDs just don't necessarily have enough sensitivity for a continuous measurement of these things. Most of the sampling systems that measure nerve agents are cumulative, where they absorb the chemical onto a surface for a little while and then make the measurements. But here we have a continuous flow through, so you just don't get a buildup of enough material to detect adequately. PCBs, polychlorinated biphenyls, used in transformers and polycyclic aromatics. PAHs, they are not volatile enough, even though you could, in principle, detect them if you got enough into the air. And many pesticides are similar in that they are not very volatile, so they're often hard. Some of them are fumigants, can be measured, like methyl bromide and methyl isothiocyanate, but a lot of the heavier pesticides that stick around on the plants are designed to be sticky, don't get enough vapor pressure to measure in ambient air with a portable PID. We have available response factors for some 450 compounds across the industry from various manufacturers. Starting from the A's, going all the way down to the V's and X's. We've got the available values for the correction factors for the 10.6 EV lamps, or the 11.7 lamps, or in some cases the 9.8 EV lamps, or 10.0. This term is used interchangeably with different manufacturers. Some call it 10.0, some call it 9.8. So those lamps are generally the same. When it says no response, there's no NR is no response. The dash just means there's no data. So without getting into this any more detail, just to show that there is a whole list of some over 400 compounds that are available. If you know what you're reading, you can correct for that the sensitivity of that particular compound and give you a direct readout of the concentration. Here's a simple way. The true concentration is the reading that you get in your ambient air sample times the factor. The factor here, let's take an example of isobutylene. You're always calibrating to isobutylene, so these factors assume you're calibrated to isobutylene, the standard calibration gas. The PID display, in this case, we're giving an example of acetaldehyde is what we're measuring, and the reading is 5 ppm. We go back to our table. Acetaldehyde, our correction factor here is 6. So we multiply our 5 times 6, and the true concentration is 30 ppm of acetaldehyde. Again, if you have a mixture, then you can't tell. But if you're measuring a single component, you can always correct for it like this. Now, most of the modern PIDs will do this calculation for you. You just simply program in which gas you're measuring, and it looks up in the table what the correction factor is, and it adjusts the reading so it will display directly in the concentration of the compound that you're measuring. So here are some applications that I guess many of you are familiar with since you're already using the instruments. Oil refineries have a range of BTEX and hydrocarbons that need to be measured for health and safety purposes, both LEL and industrial hygiene levels. In tankers, anywhere you have confined spaces, tankers sometimes need cleaning out, so diesel fuel is often available, present in the holds, or whatever the cargo is they may be carrying the solvents, hydrocarbons, ammonia, etc. Wing tanks, often people need to crawl into the wing tanks to clean them out or do maintenance. And here they're wearing a confined space entry monitor, but they're also worried about benzene exposure and BTEX while they're in the tanks. Heat exchangers, these components are diatherm is a good example, diphenyl oxide and biphenyl, about a 50-50 mixture of these two. The OSHA PEL for this is 0.5 ppm. And so you need a good sensitive detector to measure these things. One issue with measuring them is that they are often these are heavy components, and so they tend to absorb onto any tubing. So this is a general phenomenon. You can't put an extension tubing made of Tygon tubing or rubber hosing onto a PID and expect it to measure the components in there because they can be absorbed onto the tubing. I had a guy once complain that the PID wasn't working, and it took me an hour of discussing with him on the phone until I finally realized that he was trying to measure diesel fuel down a tank, and he had connected the PID to about 15 feet of Teflon, or not Teflon, but Tygon tubing, and all the diesel fuel was being absorbed in the tubing, and he wasn't getting anything into his PID. So I've gotten to switch to Teflon or metal tubing, and that will usually do the trick because those absorb a lot less. So whenever you're dealing with heavy components, boiling point compounds, you need to watch out on the sampling in particular. Some PIDs have software that allow you to do fugitive emissions testing, EPA method 21, where you go around to different valves and joints, and you need to make many measurements quickly within a few seconds because there's hundreds or thousands of sampling points that need to be done. Up here. Hazmat response is also an important one, particularly here showing how perimeter delineation is important. Here's been a big spill. These guys are in scuba gear, need personal protective equipment to keep themselves safe. These workers over here are waiting around. Are they safe? They don't have any PPE on. This guy's approaching. He's got no scuba on yet. How close can he get to this without exposing himself? And this is where the continuous readout of a PID is quite useful. You can walk around. As soon as you get it within the zone of high vapor concentrations, you know it's time to put on your PPE. So you delineate the perimeter, keep everyone out that's not in proper protective equipment. Soil remediation is another important one. Cleaning contaminated groundwater costs about $1,000 a ton. That was 30 years ago. Now it's probably $2,000 a ton. So you don't want to incinerate any more soil than you need to, or treat any more soil than you need to. So people, environmental consultants, will take representative samples from each batch, test them, screen them with the PID, just incubate the soil in a jar, pop the PID inlet into the top of the jar, see if they're getting any response by PID, and if they are, then it needs to be sent on to the lab for further testing or treated. And then those that are below a certain level can just be passed over, and the soil does not need to be treated. So it can save a lot of money that way. Paint booths, here are the common chemicals, RMEK, solvents, toluene, glycols, etc. Again, is it safe to have, do you need PPE? Is it safe to take it off or on? Fumigation is another good one. Often fumigation is done not in a little closed tarp like this, but in a big room where they actually store the fruits and vegetables and fumigate them for a day. And you need to know not only if you've added enough fumigants to verify that. You can do that with the PID, typically at 1,000 ppm or that kind of range. And you also need to know whether it's safe for the workers to go in there when it's vented out enough to load up all the fruit and ship it. Phosphine is a particular example, so if anyone has any questions about phosphine, ask me later. That has some unique properties that I don't want to get into right now. Another good application is fence line monitoring. Here we've got wireless transmission on this PID system. So they've mounted these PIDs here, a PPB level PID with a modem that transmits the data to a central location. They have several of these around the fence line, powered up by solar panels. They're also taking other samples like Suma canisters and charcoal tubes, absorbent tubes to measure other components. But this will give them an instantaneous warning, whereas this sampling system here will take a week or so to get the results back from the lab. Indoor air quality, by the new PIDs being able to measure at the PPB level, you can measure if there's an odor. You can locate the source by walking around until you can pick it up by the PID. Sometimes it's nebulous with your nose whether something is where the odor is coming from, but the PID is able to pinpoint it a lot better. And also just general levels of VOCs in indoor air. Here's an interesting application. When the Columbia Space Shuttle fell down, the fuel tank scattered through the Louisiana woodlands, and they were found here. Here's one of the fuel tanks containing hydrazine fuel, and it had been smashed, but they were cleaning it out. The hydrazine is very toxic. They were cleaning out these tanks using a little pool full of bleach, and they needed to know when these tanks are decontaminated well enough to be hauled off. So this guy's in a full protective suit and using the PID to measure if there's any residual hydrazine. It's very sensitive to hydrazine. Sorry. Another interesting application is for LEL measurements, and you wouldn't think of this. PIDs will cost a few $1,000s, so it's an expensive LEL sensor. But there are applications where the catalytic bead units are not working properly for reasons of poisons, for example, or other inhibitors. So 10% of LEL for many organic compounds is in this order of 500 to 3,000 ppm, and that's in a nice range for a PID to measure. Some examples include pulp mills that have sulfides present, and these will deactivate the catalytic bead sensors in a fairly short amount of time. And but you also have turpentine in these pulp mills, and they need to measure both the toxicity levels of the turpentine and the potential explosion limits in areas where they have high levels of this. Styrene is similar. Styrene will deactivate the catalytic beads very quickly, and so styrene plants use PIDs often for both TWA of the styrene, which is fairly toxic itself, and for LEL measurements. And there are other plants that have silicones that are strong inhibitors to catalytic bead sensors. When they have these silicones plus organic solvents present, they need something better than a catalytic bead to measure LEL. So often the case is when they have a need for the PID already, it can double as an LEL sensor. I've mentioned some of the recent improvements already. The sensitivity of the PPB levels, PIDs, goes down to, well, 0.01 ppm. The noise level is typically in the order of 5 to maybe 10 parts per billion, so you can't really measure 1 ppb accurately. And I think this is fairly general across various manufacturers. Something on the order of 10 ppb, though, is now detectable with reasonable degree of accuracy. And this becomes important for compounds like benzene, where I know some refineries that are now using 0.1 ppm as their exposure limit, even though the ACGAH levels and PEL levels are higher. So you need some accuracy down at the 10 ppb level if you're trying to measure 100 ppb. This is somewhat repetition. Some of these newer PIDs have all of these response factors built in, so you just dial them up. The linearity has been improved. Humidity effects have been largely eliminated, and less interference by methane. And the battery life, there's always improvements in batteries, and so the battery lifetime has gone up to 30 hours in some cases. I'm going to skip over this one. Here's a quick idea of what has been done with humidity compensation or lack of humidity sensitivity. Older PIDs had response both drifting high readings with high humidity is present, or interference by causing low readings. And the newer PIDs have the ability, with a shorter path length and a different style sensor, to have no effective humidity all the way up to 100%. So this is a response of 100 parts per million of isobutylene at various humidities where the concentration of isobutylene is the same. This has no compensation, and it's just a built-in inherent low sensitivity to humidity by this sensor. Whereas this PID, when there's no compensation, when this compensation is turned off, the response drops with higher humidity because there's a screening effect of the water. And they've tried to build in a compensation for this, but the compensation isn't the same for every instrument. So for this particular instrument, it overcompensated, so the readings could actually be high. I guess one argument for doing it this way is they'd rather overcompensate than undercompensate, because typically if you have a high reading, you're better off than getting a low reading. But of course, the ideal is to have no error built in at all. The methane effect, methane inhibits the response. In fact, all organic vapors have some inhibition of other measuring lower concentrations if the concentration of that inhibitor is very high. So when you get up here to about 1% of methane to 2% methane, there's an inhibition of the response to isobutylene. So here we're measuring 100 ppm isobutylene in the presence of 10,000 ppm methane, 20,000 ppm. And so the reading drops. And these different PIDs are similar. This is now the same plot, just going out to a higher range of 17–18% of methane. And so the reading drops. As long as you're down here in the, but less than 10,000 ppm, you could compensate for this error. You may have a 20% error here. But when the concentration of methane gets down here into the 3, 5, 10% range, now your error is so high that it's hard to compensate. So it's not easy to measure in natural gas. Natural gas contains some benzene and some things like heavier hydrocarbons, and if you want to measure those, it's difficult to do this by PID. You need some other sampling technique. Linearity is quite good, particularly in this range, 0 to 3,000 ppm. And by 0, I mean all the way down into the ppb range. So you can't even see that on this scale. But all the way down to 10 ppb, the response is quite linear. Modern PIDs are all pretty good in this range. When you get up to higher concentrations, now these again are the same data, increasing concentrations, and here's the reading. Up to 3,000 is quite linear. Once you start getting over that, and you're into this range of over, around 5,000, it starts to curve off. At 10,000, it's almost leveled off. Most of your readings are done down in this range, so it's not an issue. But if you've ever come up to a big storage tank or some kind of liquid source of chemical, you might observe that the readings are lower than you would expect. And here's why. As when you get over 10,000 ppm, like I said, this is again the same data as before, just expanding the scale to higher concentrations. The readings actually begin to drop at higher concentrations. And regardless of PID, this is just inherent in the photochemical nature of the photoionization process. There's just screening of light by the high concentrations of the chemical itself. And so you could have a situation where the true concentration is 60,000 ppm, but it's only reading 2,000 or so. So that's an inherent danger. If you're ever trying to measure these higher concentrations, you just need to use a dilution probe or some way of diluting the sample to get it down into the linear range here. Not a common issue, but it's sometimes an observed phenomenon. Now I'd like to move on a little bit to measuring benzene in fuel. As I mentioned before, PIDs cannot measure selectively. They can only measure the total response. If you have a mixture of various components, then you can't really detect one part of it. Benzene is a particular issue because the ACGH-TWA is so low as 0.5 ppm. And as I mentioned, some people are trying to measure 0.1 ppm at some refineries I know, whereas the exposure limit for gasoline is 300 ppm. So when you have a gasoline reading of, say, 100 ppm, you don't really know how much benzene is there. So the point here is that benzene is so much more toxic than the gasoline that you really need to measure the benzene and not the gasoline. But it's difficult because here's a graph chromatogram of all the components of a sample gasoline. Each peak here represents a component indicated over here. We have butanes, isobutanes, pentanes, hexanes. And then here's benzene number 9, that little peak in there, and you're trying to fish out that peak there out of all these other stuff because the benzene is controlling the toxicity of the whole mixture. So if this peak were twice as big or half as big, and you measured just by total PID measurement, you couldn't tell the difference because all the signal from all this other stuff overwhelms the signal from the benzene. So you need a way of avoiding these things and fishing out the benzene alone. And the way you can do this is with a PID tube combination, and a couple of manufacturers offer these, where you have a PID and you add a tube in front of it, and this is a pre-filter tube that pulls out like this. Here's how it works. Use a combination of a 10.0 EV lamp, and that gives no low response to these compounds here because their ionization energies are higher than 10.0 EV. So you select it, make it more selective by adding a 10.0 EV lamp instead of 10.6. And then the tube filters out, oxidizes these components here that have low ionization energies. That means it's easy to pull electrons off of them and easy to oxidize. And these heavy components get absorbed because they get absorbed on the medium. So even though they're not oxidizable, they're absorbed because they're heavy, and you're left with the benzene. When I first saw this being proposed, I thought it was preposterous. But I became a believer after testing this several times, and somehow this system is able to do it so that just the benzene gets through to the PID sensor. So again, you use a 10.6 EV lamp. You walk around with the PID without a tube in it, and in this total aromatic compound mode, just a 10.0 EV lamp, and it responds predominantly to aromatics in this mode. And you get a continuous readout, and if your reading is ever over 0.5 ppm, then you go ahead and insert a tube and then make a benzene-specific measurement. The benzene-specific measurement takes about a minute or two for all the components to get filtered out and into the PID until you get a stable reading on the benzene alone. So you can't make too many benzene-specific measurements because they take longer. They're not continuous. So you walk around when you get a hit, and then you put in a tube and make a measurement. These tubes are able to filter out a lot of components, up to 400 ppm toluene, 200 ppm xylene, octane, H2S, Methane's another issue. But there's no effect on the PID readings of these components, at least. Now, after you've done a benzene-specific measurement, in some cases you can continue on and actually get a 15-minute STEL reading. That's about the limit of how long you can go with one of these tubes, 15 minutes. So what will happen is, this is a closed tube, but you break open the ends here when you're making the reading, and the reagent inside here will turn color, will turn like a greenish color as it's reacting with the other components that it's filtering out. And you can go up until this line without any effect on the benzene reading. So you can measure benzene continuously for 15 minutes, depending on the background levels, but you can go up to 15 minutes, get a good STEL reading before you need to change out the tube and make another measurement. So this is new. You can now do STEL measurements with these components, or with these tube PID systems. This just shows that a test done with the tube PID system under dry conditions. It was challenged with 5 ppm benzene in dry conditions and 100% humidity. The tubes will pull out the humidity, so it won't have any effect on the readings. And then you know, again, your accuracy is pretty close to the 5 ppm, whether the air is dry or moist. We took some samples of various refineries, measuring benzene in the various systems. This was a complicated math to get these results, but we compared the laboratory results for the percentage of benzene in these different types of chemical feedstocks in a refinery, ranging from 0.86 up to 22% by volume, or mole percent, sorry. And by doing the same thing on these mixtures, measuring just benzene selectively, we came up with these numbers fairly close to the laboratory numbers. So the two PID combinations are fairly good at measuring benzene selectively in a broad, complicated mixture. We also did some field comparisons by taking, let's see, we took the two PID systems, compared them to a portable GC FID system and the Draeger CMS system, and these the standard, just laboratory standards, came out pretty close. The error ranges was about the same as a portable GC FID. And the error ranges are larger, but these are unknowns. But you compare them all to activated carbon, that tells you what the accurate correct value is. And here the error is larger, but the Draeger CMS seemed to have the biggest error of all of these. So again, it's a verification that you can do reasonable benzene measurements in actual field samples on complicated mixtures, giving benzene-specific readings. So that's all I've got. I hope I've covered what everybody needs, and I'll be happy to entertain some questions.
Yeah, actually, we had a couple that came through here, and we'll start from the beginning here. Going back to the correction factors, are the response factors different for different PID manufacturers, or are they all about the same? And if they are different, why is that?
Yeah, the short answer is they're all about the same. So especially with the 10.6 lamps and the 11.7 lamps, they're all, you know, roughly the same. If there are differences, the 10.0 lamps are made slightly differently by different manufacturers. So there can be slight differences. The reason being that the window used in the manufacture of the lamp can be slightly different quality or thickness, and that lets different amounts of certain photon or energy light through, which will affect the relative readings. But to a first approximation, they're all fairly similar.
Okay. Another question we got is, do you know how sulfuryl fluoride will respond to its PID? It's the Fumigant tritium for Vicodin.
Nah. Let me look it up, but it doesn't respond very well.
Okay.
Yeah, you need something else. Sulfuryl fluoride, Vicane, yeah. Yeah, the ionization energy is 13.0 eV, so you can't get a lamp to respond to it.
Another question is, why would the humidity response be different for different PIDs?
It's in the sensor design. The path length in the light path length, or the size of the channel, affects that. So the larger the cavity where the gas goes through, the more water vapor the light has to shine through. And it's kind of like driving with your headlights in the fog. You can see a short distance, but not very long. So, and then there's a whole other design features that some manufacturers have built in, the so-called Fentelec, which is designed to pull out the moisture effects. So yeah, it's all in the sensor design, and some of it's proprietary.
Okay. And then there was another question, if you can comment about using PIDs for mold investigations.
Yeah, it has been done, generally not terribly successfully. You can see mold, but when I've seen it done, generally you have to stick your probe right up to the mold, and then you can't see it behind a wall. And in other words, by the time you get close enough to detect it by the PID, then you usually can see it yourself. So in some circumstances, it can be helpful if you just can't locate it, to sort of do a screening and searching for it. It might help you locate the hot spots if it's really bad. But if it's sort of minor, then it doesn't work that well.
Okay. I think we've run out of questions. So, Werner, thank you very much for your time. Everyone who's called in, thank you for your time. We are going to make this recording available in the training center at RAECO.com. So if you wanted to share this with a coworker or someone else you think it may have interest, you can send them that way. So again, thank you very much, and have a great day.
All right.